All right, I want to talk just a little bit about how do we know the Pythagorean theorem is true? And one of the answers is, well, forever ago somebody decided, well, this is true and we're going to roll with it. And that's the way that most people see it, and that's the way, it works. But I want to show you a couple proofs to show why it works. So for starters, this is the proof that is accredited to Pythagoras. Who knows if he actually did it, but it's one that was around in that time. So we start off by drawing a box. 1, 2, 3, 4, 5. I want it to be 5 units long for ease of the rest of the thing. So we draw a box, or a square rather. And I'm going to put a dot 2 spaces from the left. It doesn't have to be 2 spaces, but it makes the picture a little bit prettier. So we're going to label these A. Here, let me change my pen size. A and B. A and B. A and B. A and B. And these are arbitrary variables, right? So that point could be swung to the left or right, but it would have to do that on all 4 sides, right? So the big thing about me wanting it to be on the grid line like that is just so that my picture looks correct. Next up, we're going to draw a square on the inside. We're going to use the orange dots as our corners. 1, 2, 3, 4. Oops, that did not work out. Let me turn off the shape shader. 1, 2, 3, 4. All right, that'll work. We're going to label the sides of the smaller square C. Now we're going to do some fancy algebra with their areas. So none of this is very specific. There's no numbers in it, which is why it's able to be a proof. It's not like a special case scenario. It's true all the time. So the area of the big square, well, that's base times height. The base is going to be A plus B. And base times height, they're the same thing, so we can just say squared. The area of the small square is C squared. The area of the triangle, I'm just going to do it like that, is 1/2 A times B. Now let's look at this a little bit. Here we have, here is a right triangle, because we said that it's a square. And we have side length B, A, and C, or A, B, and C, Now we're going to say, well, there are 4 triangles and 1 small square, all inside of the big square. So we should be able to say the area of the big square equals the area of the small square plus 4 times the area of the triangle, right? So we said the small square plus 4 triangle areas is going to be the big square area. So we're going to plug all that in and see what we can get. The area of the big box is A plus B squared. The area of the small one is C squared. And then we have 4 times the quantity 1/2 A times B. Now, A plus B squared will turn into A squared plus 2AB plus B squared. On the right side, we're going to have C squared plus, well, the 4 and the 1/2 turns into just a plain old 2. 2AB. We have a 2AB on both sides, so let's cancel those out. Let's subtract by 2AB, and they just go away. And I'm left with A squared plus B squared equals C squared, which is our Pythagorean theorem. A lot of the times, whenever I would do proofs for my real college math classes, you always would do a little box at the end. I don't know who decided that that's what we did, but that's what we did. So And that's supposed to be a prettier box than that. There's our box. So there's our proof. We started off with nothing, and we were able to say, well, always, always, a squared plus b squared is c squared whenever we're dealing with a right triangle. All right, so that's one proof. And let's look at just another one. This one's Garfield's proof. This is the President Garfield's proof. So we'll start off by drawing a trapezoid. All right. So that's a trapezoid because the left and the right sides are parallel. They're straight up and down. So we need to put an arbitrary point on there. We're going to say, well, there's our A's and here's our B's. Right? We can connect the dots there. And now we have two right triangles. We're going to call this triangle 1, this triangle 2, and this triangle 3. All right, just a second. Oh, I did something wrong here. I apologize. Let me draw the picture again. I wasn't very off, but I think it would just be faster to redraw it. All right, there we are. They aren't supposed to go together. There, and then here's our C's. Oops, I apologize. All right, what I changed here was these guys are now just slightly different than they were. And now we have our C's, triangle 1, 2, and 3. Here's our 3 right angles. All right, now that looks a little bit better. So the area of the trapezoid, we're still going to try to use our area formulas. Area of the trapezoid is going to be the average of the bases. So we take a plus b over 2 times the height. The height is also going to be a plus b. The area of triangle 1 is going to be 1/2 a b, 1/2 base times height. The area of triangle number 2 is going to be 1/2 c squared, because its legs are both c. And the area of triangle number 3 is going to be, again, 1/2 a b. All right, yeah. So we can say, well, the area of the trapezoid is equal to the area of triangle 1 plus the area of triangle 2 plus the area of triangle 3. And you should be able to see what we're going to be doing next. We're going to plug in and try to solve. So I'm going to plug in a plus b over 2 times a plus b equals 1/2 ab plus 1/2 c squared plus 1/2 ab. All right, there we are. Now, we should notice that there's a fraction of 1/2 all the way through this. Let's multiply everything by 2 and just get rid of it. So now we're going to have a plus b equals ab plus c squared plus ab. Now, if we distribute out that left side, we're going to have a squared plus 2ab plus b squared. And if we combine like terms on the right side, we're going to have c squared plus 2ab. Just like last time, we have 2ab on both sides and they can cancel. And we have a squared plus b squared equals c squared. And we're done. Alrighty, there we are.